Okay, topic 21.1, a little bit more detail on spectroscopic techniques, notably NMR and X-ray crystallography. So we saw in the standard level section this idea of looking at a molecule and seeing how many hydrogen environments there were, and that would tell us how many peaks we'd expect, or signals, and we would also be able to tell from the area underneath each of those signals how many hydrogens were in that particular environment. And we also mentioned the fact that we had this internal standard tetramethylsilane, which looks like this, and that is set as 0, and then we've got all these shifts based relative to that. But we learned number of environments, how many H's were in each environment, and we could look at our low resolution trace and see that. Now, what we need to be moving on to is this idea of coupling, where hydrogens on one atom are affected by the hydrogens on an adjacent atom. So if we take this one here, because we can see in the example here something a little bit funny happens with the OH, but if we take this CH3 group here, this is one of our environments, it is next to two other protons, right? It's next to a carbon that's attached to two other protons. And what we find is that the peak, the signal, due to this, splits into 3 as a result, because we follow this n+1 rule. So it's 2 plus 1. So that peak splits into a triplet, like that. And we can try drawing one ourselves for this ester. So if we draw out the structure of the ester first, we should be able to fathom that it looks like this. And straight away we can see, well, there's going to be 3 environments. We'd expect 3 signals. 1, 2, 3. 1, 2, 3. And in terms of their areas under them, signal heights, if you like, the integration trace heights, we'd expect them also to be in a 1 to 2 to 3 ratio, because there's 1 in that, 2 in that, 3 in that. Now what would our trace look like? Well, at 0, as ever, we've got our tetramethylsilane. And then if we look in our data booklet, we can see roughly where these environments should be. Now I couldn't see this one in the book, but certainly that CH3, we'd expect to see something around about there, and that's a 3-fold peak, so we'll give that quite a big one. And this group here, I think, struggling to see it, but I believe it's around about there. So if this one is at about 1, that one's going to be around about 4, and again it's going to be a little bit smaller than the other one because there's only 2 hydrogens. This one, as I say, couldn't find on here, but it's close to these oxygens. We use the term de-shielded, and I think it's going to be further down this end of the spectrum, but a littler peak because there's only 1 there. So that would be our kind of low resolution spectrum. Now in terms of using this splitting rule, this one is next to a carbon with no hydrogens on, so it's going to exist as a singlet. Right? Singlet peak. Oh, I'm making a bit of a mess of that. Let's try that again. A singlet peak. So it would just be a line like that. This one that's occurring at 4 is next to 3, so we expect it to be, remember, n+1. We would expect it to then split into 4, a quartet. So it looks like that. And then this one, which is adjacent to 2 there, so n+1, 2 plus 1 is 3, we'd expect that one to exist as a triplet. So the high resolution on top looks like that. X-ray crystallography involves firing X-rays at a crystal. So we've got to make a crystal of our substance first, and then looking at a diffraction pattern. So the X-rays are diffracted, their direction is changed by the bonds, by the atoms, and by doing some rather complicated maths involving the wavelength and the angles that things are moving at, we can get a diffraction pattern, and interpreting that diffraction pattern using the maths, we can get an indication of what is present. And at a very basic level, one of the things that it's going to give us is bond lengths. And so by looking at expected bond lengths from data booklets, we can maybe identify what types of bonding we have within our molecule. Right, that's what we've covered.